Hello? Amrit? Hello? Hello, am I audible? Hello? Okay. So, since you are the only one here right now, maybe we can start with some doubts if you have. Are you speaking something? I'm not able to hear. Okay. Maybe we'll wait for some 2 or 3 minutes. Let some more people join. Is that alright? Okay. Today, actually, I was planning to show some demo codes on some of the concepts that we studied in this week. So, I'll share some Colab notebooks. Are you familiar with Colab notebook? Yeah. Okay. So I'll share a link to a Colab notebook and uh, just I'm not able to hear you actually. Yeah. Uh, mm, okay. Uh, so we have two more joinees, Chandni and Sri Bhanu. If you guys have any doubts, we'll start with doubts and then today I'm planning to show two demo codes on two of the concepts that we studied in this course content, this week's course. We'll first go over the doubts and then maybe we'll shift to the codes. Uh, Amritansh, I think I'm still not able to hear you. Your mic is unmuted, but I'm still not able to hear you. Is anyone else able to hear him? Okay, 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 fine. Okay, yeah, sure. So I'm waiting for some doubts for first 10 minutes, and then if there are no doubts on the course content, we will shift to the collab notebooks. Okay, I guess there are no doubts. So maybe I'll give you a brief description of the demos that we are going to look at today. So the first demo that we'll be looking at is an application of this convolution and transpose convolution network that we saw in week 6 and week 7. So how those operations actually help us in an application for denoising of images. So, and this we will see on a dummy data set for like so that it will run faster, and we can show and discuss the results also. So we will look at this application on MNIST dataset. So as you know, the MNIST dataset is actually a very common toy dataset that is popular with CNN applications. So you'll be having images of handwritten digits in grayscale images basically. So and the popular task that people try to do with this is they try different convolution neural networks and try to classify these digits into their corresponding classes. So and basically that's the usual task, but today what we are going to look at is a different operation, different task actually. So we will be looking at denoising a set of images of this data set. So what we'll be doing is you will be having given some images of handwritten digits, and we'll be adding artificially some noise on top of it, and we'll make the image more basically noisy, and it will be difficult to identify the exact digit that is written below it. But we'll train a network that will take input this noisy image, and it will also have the real real image without the noise as the reference, and it is basically a supervised learning process. So we will look at the network's output. So our network that we will be training, we'll look at that network's output, and that should be ideally similar to the original image without the noise. So that is our goal. So whether we can achieve this with our network is what we are trying to see. So that is the idea of the first demo. And the second thing that we also studied in this week's content was the idea of transfer learning. So in transfer learning, what we essentially were trying to do is we have these large models which have been already trained on lots of data, and we maybe have a smaller subset or some other type of data, and we want to utilize the weights or the things that these large models have learned from the bigger data set, and only so we will fix all the previous layers. So let's say you are using something like a ResNet or VGG, which are some popular networks that we saw in the course in the previous week. So the idea was there that your input image, when it passes through either of these ResNet or VGG, it will give you a class, but these models that were trained on some different data set, so they were trained on the ImageNet data set, and which was classifying an input image into one of the 1,000 classes. But let's say we have a different data set with some different objects in it, and our goal is now to learn, let's say in this specific case we are actually going to look at something called the CIFAR dataset, and in this there are only 10 classes. So we will use the trained model on the ImageNet dataset, the ResNet model, and we will retrain it or fine tune it for this CIFAR dataset, and we'll see how that works out. And so essentially in general, when we were looking at this ResNet or VGG model, we had bunch of convolution part, and then at the end we had this simple fully connected layers, right? So a bunch of fully connected layers, and there was a classification layer at the end, and these were all convolutions, and perhaps a bunch of convolutions and poolings and so on. So I'm clubbing all of that together. So these models, they only had the last few layers of these models were actually the ones which had the most number of parameters, and the previous part, all this previous part, that convolution part, it was actually learning some of the general stuff about the image. So in an image, let's say there is a I don't know, maybe a tree. So something like the features of the borders between the ground and the sky, so the horizon. So basically this border, or the trees border and the leaves border and so on. So these kind of stuff is what the previous convolution layers were learning, and in fact the very starting layers were actually learning these basic stuffs, and few layers later down the line were actually learning a combination of these features. So some more complex features like so if the starting layers, for example, were learning some edges like this, so maybe later down the layer will actually understand that this can actually be interpreted as a leaf or some so it is not exactly the way it works, but we can imagine it something similar happening. So the layers at the start were actually the ones that were learning basic features. Of the image, and then more complex features were learned later down the line. And at the very end, we were actually doing the once we have like shrunk down this entire image, or this entire data set, actually we have found its representation in a much lower dimensional space. For example, in ResNet and VGG, that could be some 512 dimensional vector, and at the end we were applying two more fully connected layers or so, and finally getting our classification. So in this case of transfer learning, we would like all the thing that the model has learned up till this point. So all these basic parts of the tech images and the more complex features, but we only want to change the later part, which is these fully connected layers part, which was doing the majority of the classification work, because we now have a different set of classes. So we want to change that part, and we'll see how that can be actually implemented with the Pytorch. And yeah, that's it. In fact, I will show you demo with ResNet today, and I will ask you guys to try it with VGG in the same manner. Is that okay? Any doubts till this point? Any doubts? Are you guys excited to see this happening? Okay, we have one person who is excited. Others are not excited, I guess. But yeah, we'll still go with it. So the first one we will look at is the denoising application. This is only going to use convolution and the transpose convolution. So we will basically use only these two layers, but you'll see that is sufficient to for our task. So I will stop sharing my tab. Is my screen visible? I'm sharing a Colab notebook. Okay, so maybe I should share this link. So if you click on that link, I think it should lead you to the code. I hope everyone here is familiar how to run a Colab notebook, right? If not, I will explain that part first. Is anyone here who is new to Colab? I guess not. Okay. So we'll look at this demo code, and so here I've written it as unit, but this is not actually a unit architecture. The real unit architecture is what you saw in the course this week. This is actually just it's a much simplified version of what a unit would actually do. So in the initial part we are only defining the network, but we'll come to this part a little later. As I described in the just a while ago, so here we actually are so this is the function that is adding some noise to our input. So if an image is sent in, it will add some noise, which is like a random noise basically, at same size as the input image. And so since these are grayscale images, there is only 0 and 1 input, 0 and 1 values of the pixels. So this type of noise of adding 0 and 1 is called salt and pepper noise. So you basically, so this 0 value is called pepper noise and 1 value is called salt noise. And in general, so the images that we want to use, they have to be in this tensor format. So Pytorch actually works with tensors. So it's similar to matrices, but they have this specific data structure in which they expect the inputs to the various layers that we define them to have. So this is a transform that will always convert whatever you send in to a tensor form. And our training dataset is actually this MLESA dataset. Pytorch has some inbuilt datasets present in it, so you can actually get this MLESA dataset in this using this line, and you can use it. So this train dataset is actually an object that is given as output from this function. And then this data loader. So in general, what we try to do is instead of loading the entire data set at once, so if the training data set had some 60,000 images, we would not want to load all of them at once into our RAM, so else the laptop would crash. So instead of doing that, what we will do is we will load them in batches. So here we are loading in batches of 32, and so this data loader will actually randomly take 32 images from our complete data, and it will send them out, and those is what you will use at one particular time step to update your gradients. So I will come to the how we are making this model later, but so once we have defined a class for our model, we will create this object of that class model, and here we are defining our loss function as the mean squared error loss. So as I said, we'll be having both the real image and so the input for the model will actually be the image added with noise, and the output is expected to be the noise free image. So whatever our model will end up predicting, we want to see the error of that with the real noise free image. So basically that's why we are defining the loss function as mean squared error this time. Okay, so this is not a classification problem, that's why the there is a change in the loss function here. And the optimization algorithm, we are still using the Adam, and we want to update the parameters of our model, and we are using learning rate of 0.001. We'll be using 5 epochs. We'll be training our, so yeah, an epoch will ensure that in one epoch the entire training data set will be seen by the model, at least full data set will be seen at least once. So that is the idea of an epoch. And our train loader, which was our this data loader thing, which was picking out 30 to 32 images every batch, and so we'll train our model only on those 32 images initially at that time step, calculate our loss, print it out, and we'll also see the, so after every 10 mini batches, 100, after every 100 mini batches, we are actually displaying what the model actually was working with and how well it started performing. Okay. So maybe I will go through this part of the code a bit later. We'll first go over the main model itself. Okay. So far, any doubts? I'll wait for some 2 minutes. I hope everyone is able to access the code. If someone can give a thumbs up, that will be great. Okay, thank you. Okay, so we'll discuss the main architecture of the model that we are implementing here. So as we saw in the lecture, so our our input, so we are only keeping a single encoder and a decoder part in our model for now. And so what we will do is, through our encoder, we will change the image, take our input image, and then we'll try to reduce its size basically. And from this reduced size, we will extend it and convert it back to our output size. And the hope is that throughout this process of the convolution and the transpose convolution, the model will actually learn what is the real digit part of the image and what is the background, and it will properly separate out the and it will properly remove the noise part of the image. Okay. So in general, these MNIST images, they are of size 28 cross 28, and so the first layer that we are placing here is a convolution layer. I'll just tell what is the first parameter. So the first parameter is actually telling the input channels. So in our in a grayscale image, there is only one channel as the input, so that's why this is 1. And we are asking the model to give out, so output channels, we want them to be 64. We are choosing a kernel size of 3 and padding of 1. For now, almost the entire of this model is actually like it's just arbitrary choice of kernel size and hyperparameters. Basically, all of these hyperparameters have been chosen arbitrarily. You can explore different values here, so you can change the number of kernels that have to you want them to pass. So but you just have to make sure that whatever you put here, so if you put 32 here, you have to ensure that here also you will put 32. So because the output channels of the first layer should be the input channels for the next one. So just make sure of that. And so after the two convolutions, because we have put kernel size 1 and padding 1, that is actually ensuring that the actual size of the image, so that 28 cross 28, that part is not changing in the convolution part. But once we do a max pooling with kernel size 2 stride 2, that is actually making the image size to shrink. So we'll ultimately at the end of our encoder block, we will actually have a 14 cross 14 image, but we will have 64 channels because this was 64. Okay, any doubt till this point?
Mr. Govind, how do we decide on the number of channels? See, the 64 is there.
Yeah, that is actually a, so that is a hyperparameter for you.
Yeah, yeah, hyperparameter actually, what will change? I have a doubt actually. See, when you have a kernel size, yeah, we know what it does. It
Hmm.
just slides over the input image and it gets the output.
Hmm.
But how it affects this depth of that thing, that 64?
Okay, okay.
So, do we have that 64 times that kernel values?
Yeah, actually we have that. So you are
Mm.
not putting just one kernel. So it's not just
Okay.
one kernel of size 3 cross 3.
So 64 different kernels.
Yeah.
And see, if you have 64 different kernels, that means your total combination of your 3 into 3 must be more than 64, right?
No, the kernel size itself is 3 cross 3. That will
3.
run over your entire 28 cross 28 image. That will give you out one smaller image. I mean, here since the padding is also there, that will
Yeah,
again give you a
that is
28 cross
correct.
28.
That is correct. See, one kernel is having 3 into 3 unique parameters, values, right?
Yeah,
And the second one will have 3 into 3 unique values.
correct.
Okay, and each cell can take any value.
Yeah, I mean, that is
Okay,
essentially what your
okay,
model is expected to learn. So those
okay, okay,
numbers in the
right.
3 cross 3 kernel.
Okay,
So
then in the case you can have as many number of
yeah,
kernels as
yeah.
well. Okay, okay.
So our actual goal with having this number over here is actually to see. So one kernel might be. Maybe I should switch to the tab for a while. Hmm. I hope my
Yeah,
notes
yeah,
is visible.
yes.
Yeah. So our goal with this kernels is actually to ensure that. So let's say this was my 28 cross 28 input image. And then let's say I chose one particular kernel of size 3 cross 3. This entire kernel will, as you know, it will go over this image like this, then like this, then like this. It will keep on running over the entire image, and every time you run over it, since the first image that we started with had only one channel, it is actually some when it runs over this part of the image which was padded. So as you saw in the code, we had put padding 1. So this is actually that 3 cross 3 first first part of the process. This will ultimately give you out of the output image. It will again give you out the first box basically. So once the kernel shifts, it will give you the next box.
Yeah, yeah. See, that much is clear.
Hmm.
Yeah, what I was asking is 28 different channels are there, right? So that means that your filter values itself will change 23, 28 times, right? 24 or
No, 64. Yeah.
yeah, sorry.
Yeah.
64 filters means 60. So at least one value of the your filter has to change, correct?
Yeah. In fact, so these 3 cross 3 kernels that we are seeing,
Yeah,
that entire thing is, so right now we ran through this particular one.
yeah,
You will
correct.
have another one with different 3 cross 3 values,
Yes, okay.
and that will run over the entire image,
Yeah,
and then you will
like
get,
that 64.
yeah, like that, 64 of them.
Okay.
And so once this runs over the entire image, you will get another 28 cross 28.
Yeah, and then exact 3 into 3, that 9 values, so the program will find out, right?
Yeah, your goal of your
Yeah,
convolution network is actually to learn these 3 cross 3, all of them. So there
yeah,
are 64 of them, we want to learn all 64 of them.
okay.
Okay. Yeah, that was a good question. So actually what I wanted to also tell was that, so let's say you might wonder, like, why are we having these different values of 3 cross 3 kernels. So if if imagine one particular 3 cross 3 kernel was something like this, so it was 1 0 0 1 1 0 0 0 0. Okay.
Yeah,
And if you ran this over a image, so let's say there were some numbers below, so this was, let's say, your original image on which you are running this particular 3 cross 3 kernel. Okay, so this had some values over here. When you put this kernel on this part of the image, the first block, it will
yeah,
output you what is the sum of these three, right?
correct.
And that will go in your channel, the output channel's first block.
Yes.
But let's say you had a different kernel which was like this, which was having 1 at the diagonals. Okay, so then it would output you the sum of these three in the output,
Okay.
right?
Yeah,
So your ultimate goal is actually, so in fact it can be shown that these, whatever I just showed here, 1 1 in the along an column or along a row or along diagonals, that is actually different type of edges that we want our so that is what the lower level features that I talked about here. So the lower level features that your network wants to learn are actually these edges.
yeah. How do we know if you put one like that, it will catch the edges?
Okay. So maybe we should take some simple example.
The first class also, the instructor was telling that 1 minus 1, if you run the filter 1 minus 1, it will you will get the edges, but it was not explained.
Okay, so we will take some like a simplified image as our input image. So let's say this was your input image. Okay. Now this image is having, for example, so I have maybe taken a very zoomed view of the real image. You can assume that also. So this is actually a 5 cross 5, right? Or maybe I put 5 cross 6. We actually should remove that. No, yeah, put 5 cross 6. Oops. So if this was your input image and there were ones along this second column and rest of the entries were, let's say, 0. Now assume that you applied a padding also, so that we will get the output of the same size as, so output should also be 5 cross 5. That is what we actually want. So assume that the outer border that I have drawn is also full of zeros, but the inner 5 cross 5 is what your original image was. Okay.
Yeah.
So now if I apply this particular filter, so this 1 1 1 1 0 0, this one, okay,
Mm.
if I apply it over this part,
Mm.
as I keep sliding it, okay,
Yeah.
so what
Okay.
will happen, initially it is summing up these three values, then it will
Mm.
sum these three values, at some point it will sum over here.
Yeah.
So of my output, the first number is 0 because it summed over this thing, then it summed over this thing, so the second number is also 0.
Okay.
But when it came over here,
Yeah.
so that time I got 2, right, because
Okay.
this was my input, it went on this 1
Mm.
1, so here 1 was there, here 1 was there, here 1 was there, 0 0 0 0, okay, so I
Mm.
got a 2. Now when I slided it further, I will again start getting zeros,
Mm. Okay.
right. So maybe I should draw extra here also. Again the same thing when you do on the lower thing, you will again get this similar
Okay,
right.
fine. See, just a minute.
Mm-hmm.
Your input image, you have put the ones in a single column.
Yeah,
So that means in your image, you have a very sharp edge. Let us say that
yeah.
one of the one is just left side or the right side, or slightly smudged.
You mean this part?
No, no. In your input, you have put 1 1 1 1 5. That 5 ones, right?
Yeah,
That actually that represents a image which is having very sharp edge, right?
yeah, exactly. It will look like, uh,
On
so
straight line.
this is white and
Yeah.
this is black, so it will look like something like this.
Okay. So if one of that one is slightly right side,
Okay.
let us say,
Mm-hmm.
see your 1 2 3, your third row,
Oh,
okay,
oh shit.
yeah, is not in the same line but in the next line. So will the filter catch that one or cannot catch?
So the thing is, if this filter won't catch it, I mean, this particular filter will still catch something similar. So even if the one was over here, ah,
Oh,
uh,
yeah,
even if the one was here,
yeah, correct. Yeah,
so this was the one actually.
yeah.
So even if the one was here, what the
Okay,
filter would capture will be, it will capture oh, in fact I actually messed this up, so this would actually be 3.
okay.
Yeah,
So
so
instead of becoming three, it will become two, right?
exactly,
Okay, okay. So
that's what.
so still it will catch the prominent
Yeah,
trend.
so it will basically find out uh, what is in the image, and
Okay.
our ultimate goal is that, so we keep on passing this sort of patterns
Mm.
throughout the layers, and ultimately it will understand that that means an edge. So the network has no idea what an vertical edge, what a horizontal edge, or of
Yeah.
any of that sort, what that means. But it's actually our understanding that what those kernels might be representing. Okay,
Okay, okay. Thank you. Thank you.
so I will switch back to the
Yeah, sure, sure.
code.
So,
Okay, so we I hope the code is visible again.
yeah, yeah.
Yeah, so that's what we did here. So we applied a convolution layer. uh, it is single input because it was grayscale, and we are expecting an output of 64 channels, and the kernel size is 3 cross 3, padding is 1. and then we are, so this part is doing the non-linear activation. So here we are using ReLU activation. You can explore different activations also. That is also a hyperparameter for you to work with, but ReLU is probably most often used on these kind of applications. And then we are applying another convolution layer. This is still having kernel size 3 and padding 1. That's why our output at this point, so before the max pooling layer, we are still having a output of 28 cross 28 cross 64 because of the number of channels. So what I am writing here is actually not the way the tensor is written. The if you had to write how a tensor would be represented is actually
Reverse.
yeah, it goes actually reverse, and the first entry here will actually when it is running through the training loop, this will actually represent the batch size, then it will put the number of channels, and then the number of size of the images. Okay, so maybe I should okay, and once we do the pooling, this will actually make it 14 14 64. Okay, now when we did this part, we actually shrink the size, and we are going to now apply on this shrinked thing, we are applying a convolution layer and another convolution layer. We are still keeping kernel size and padding 1. So at the end of this part, here also our output is still 14 14 64. But when we now do a transpose convolution, here we expect our output to be same size as our input, 28 28 64.
Yeah.
28 28 actually 1, because the output channel is 1 here. Okay, so this is actually a question for you guys. What should be the kernel size and the stride that we put here, so that will ensure that our output will come out to be the correct size? So 28 28 1. So 1 is actually going to come from this part, so you just have to figure out how to get that 28 28 from our 14 14.
14. So, so for that also a formula is there, right?
Exactly, yeah.
Yeah, that for that formula.
Two two. We have got one answer. We'll wait for 2 minutes for everyone to calculate.
Yeah, I forgot that formula.
Yeah, no.
So it runs reverse to this formula actually.
Correct.
Just a minute. Just give me some 2 minutes.
Yeah, sure, sure.
Yes. think stride to
Hmm.
filter to padding 0.
Correct. So, uh, is everyone getting that? Why we got the values 2 2? If anyone has doubts, we'll cover that. Okay. So I'm assuming everyone is comfortable with that. So that is the correct answer. We can actually use 2 2. And in fact, there are the many number of combinations that we can use, but uh, to keep it small, we basically better use 2 2. Okay, so we'll go with this thing, and so this is our definition of our model. We are actually having two blocks. One is the encoder block, and one is the decoder block. So what we will do is, uh, so in this here we are actually importing uh, the torch.nn. So this is actually having uh, an implementation of this. So nn.module is actually a class defined in uh, Pytorch, and what we are doing is we are inheriting from that class. Okay, so this unit class that we are calling is actually we can say it is using the nn.module as its reference. Okay, and in this nn.module there is a forward function. So that is the main thing that will uh, be used when training happens. Okay, so forward function basically tells whatever will be my input to my model, what should the output be. So that is what the forward function will basically summarize. So what we are doing is, if x was an image which was a 28 cross 28 cross 1 image, if I pass through my encoder here, I will get some output x1. I'll pass that x1 through my decoder, and I will get some x2, and x2 is my supposed output of my function. Okay, the model. So that is what this forward function is actually for about. Okay, and as I covered about this salt pepper noise, and the data loader, so I think we can move to the training loop. So what we are doing is, we are running the entire training process for 5 epochs, and in every epoch it will run through the entire training data, and we are going to from this train loader that we saw in batches, we are taking 32 images in batches, and that 32 to 32 batches will cover the entire data set. Okay, so what happens when one batch comes in? We take that one batch, we are calling that inputs. We are adding this salt pepper noise to the input basically, and then so before our training process for this loop starts, we need to initialize our gradients, right? So this is basically setting the entire gradients to 0, and then our backward, when we are doing the optimization step, we will calculate the gradients and update our weights. So before we do that step, we are just setting it to 0. Then here we are calculating the output of our model. So as you can see here, the noisy inputs is what goes into the model, and out comes our output. Okay, and Then we are checking the loss between our output and the real inputs. So the real inputs were the ones which were without the noise. We added the noise on these noisy inputs. So we are computing the loss based on that, and then we are, yeah, this is the step where we are calculating our gradients and stuff, and here we are optimizing our kernel, the weights in our kernels, and we are just adding the loss. So this is just for printing purpose. So I will just try to run this. So when you may run this, I'm not sure. So yeah, here I have included.
See, for running this one,
Mhm.
we need to install any software.
No,
This
no, uh,
Pytorch.
no. When you are running in Colab Notebook, you don't need to install anything.
Okay, so it will be running in your system, right?
Right now, what I did was, instead of running it on the Colab Notebook, I have connected it to my local laptop. That's why you will see here connected local. But
Okay.
in your case, you can actually run it on the cloud itself. The
See, okay, this is possible only during this session, or
No,
after
no.
some time also I can run on the cloud.
Yeah, you can anytime run on the cloud.
Okay, I just open this thing,
Mhm.
and then I can run, right?
So, so in this Colab Notebook, in your version, you must be seeing at the top here, copy to drive.
Oh, yes.
Yeah. So when you click that, it will
Mm.
make a copy of this entire notebook in your Google Drive,
Yeah, yeah. Okay,
and from there you can access it anytime.
okay, fine. Okay. Thank
Okay. So yeah, the code has started to run. Uh, we'll see that in first few iterations, it's not doing the job pretty well. So this was our noisy input that we sent to the model, and these were our original images. Uh, and initially the model has not learnt the correct way to denoise it, but it is still doing a pretty decent job. But it's still, it in fact, for a part of it, it actually thinks the noise is also a part of the main image. So uh, some of it is still, it is trying to learn, but as you progress through the iterations, I think you'll notice that it improves a lot. So here in the starting of the training process, it will look a bit blurry. So it has not really learned that to completely separate the background
you.
from the digit. But as you go more and more, so this is still we are still in the first epoch.
Mhm.
So in fact, I think I'm, yeah. Oh, okay. It's still running. So you can try and run it on on your systems also, and uh, you can check how this performs. Okay. So by the end of the process, it will pretty much uh, do the
Yeah.
denoising part very well. Okay. So that concludes our first demo. If anyone has any doubts at this point, we'll cover those and then we'll move on to the next demo. This will keep running, so it will take quite a bit of time actually. Why are the loss values at a particular iteration different when I run it? Yeah, I mean, when in your case, the initialization of the weights might be different. So Yeah, it is also because of the randomness in the batches. So at each batch, what images your model is seeing and what my model is seeing might not, when I am running it, might not be the same thing. So at each batch, your data set might be seeing different images. I mean, your model might be seeing different images. Mine might be seeing different images. The noise is also added randomly, so that is also creating a variation in the training process. Yeah. So I will stop this process now for the next implementation. Okay. So you can, if you want, you can keep it running. Okay. So we'll now switch to the second demo. Is my screen visible?
Yes, yes.
Yeah. So this is our second demo for today. We are going to look at using Pytorch how we can implement this transfer learning, and so I will give you the overview of how we will do this process, and for demo I will use this ResNet model, and we will keep around last half an hour for you to try out, and instead of ResNet you will be trying VGG network, which you also saw in the previous week's content. Okay. So we will briefly go over the code. So this is just the importing of all the content. So in general, when we are training these models, we actually would want to use the GPU to train them, and that will increase the, I mean, make the training process much faster. So usually, uh, with this torch.device, you can actually set the device, and it will basically return CUDA if your system has GPU, and else it will return CPU. So in my laptop, I've connected it to my local system. That's why it will now show my onboard GPU. So if I here add one more cell and just print device, so it has written CUDA. So that means the code is able to access the GPU on my system. In your case, when you are running this on Google Colab, you can actually here you will have an option of change runtime type. Okay. If you click on that, by default it will be set to CPU, but you can change it to T4 GPU or TPU. So TPU is also a type of GPU called tensor processing units, and you can switch to them, and that will fasten your training process. Okay, but for now I will be running this with my local server system only. The thing is, in general, when the Google Colab is a bit slow when it is taking dataset, basically reading the dataset. So the CPU process part itself is a bit slow. But when we run it locally, it runs a bit faster. So for demo, I'm going with the local. Then, as I described before, so our task in this demo is actually to use the trained model, the ResNet model, which was trained on the ImageNet dataset, which had 1,000 classes, but we want to use it to classify some different dataset, which is this CFAR dataset that you will see later. So in that dataset, there are only 10 classes, and they are not the same as our ImageNet classes. They might be named differently or something. So in this case, so we want to retrain our model, do the fine tuning for the last few layers, and let it learn that part, and then let's see how the performance for that new model works out. Okay. So the number of classes for this is just 10, and the learning rate we have set to 1e minus 3. Batch size we have set to 1024. So each batch will see 1024 images, and we have set the epochs to 50. Okay. So so this Pytorch actually has some of these. In fact, all the models that we saw in the course, they are already trained, and they're trained models with the weights. They are actually present in this torch vision dot models. So you can access any of those models directly using this command. So these were trained on the ImageNet dataset. Okay, so those trained models are directly available to you. So we are basically importing that in our code here. In your case, it might show downloading or something. Since I already ran this, it's already saved in my system. And we are taking the default weights of the model and having them here. So if I now want to see what were the layers and how was the model made, I can actually print that model, and it will show me what was the content of this model. So this is particularly ResNet 18. In that there were a bunch of, so in fact you can actually go through this and see what all layers were included in this ResNet model. Okay, but what you will notice here is that towards the end, so once our entire model has been so there is all these blocks of convolutions. Okay, so there are layer 1, layer 2, layer 3, layer 4. All of these are blocks of convolution networks only, but at the end we are having here the fully connected layer, and it's not showing the classification layer actually. Okay, fine, doesn't matter. So at the end we are having this pooling layer and a fully connected layer, and as you can see, the output features in this case were 1000. So that is the output classes of your ImageNet dataset, and just before that we had 512 input features. So when we are doing the fine tuning and transfer learning, we should also make sure that the part that you replace from the original model, that will also take input as 512 only, and the output is what you actually want to later change. Okay, so with this part we are actually saying that whatever are the parameters of this ResNet model, uh, we don't want to change them during the training process. That's why we are setting this requires guard parameter to false. So when the training process is going to happen, these parameters will be fixed values. So in fact, right now it is taking all the parameters, including these things, as fixed values, but we are going to reassign those parts here, and as you will see here, so now we changed the last part. So this average pool layer, which was this one, we have kept it as identity because we don't want anything to happen over there right now. So whatever our convolution layer returned, we are going to we know that it has to take input as for the later classification part. We want the input to be 512 features, and our output to be this number of classes. So just for fun, I have put one one fully connected layer with 512 input and 100 output, then the activation, and then this again 100 cross num classes. So this num classes is going to be 10. So you got in 512, you made it smaller, even smaller to 100, and then you made it smaller to 10. That is what is happening over here. So you can play around with this part ideally, and so again we are setting a last part as identity. So this actually doesn't have the another layer called classifier, but you will see in the VGG network there is a classifier layer also, which you might change and according to what you want to do. And with this command we are sending so as you saw before, the device at the top here, this was my device, which was a GPU machine. Okay, and what we are doing is we are passing this entire model and we are sending it to the GPU part for computation. So this this line actually makes sure that you will run all the computations on GPU. Okay, so that is important line. I'll just hide the output. Yeah. Then we are just running to get our data set. So this is the CFAR10 dataset, which has 10 different classes, and we are transforming that entire dataset to tensor form because we are implementing everything in Pytorch, and we are putting this data loader that we saw in the previous code also. So here we are going to set batch size as batch size, which was we set it here as 1024. So that's the, so this will be our train loader, and just for the viewing purpose, we are viewing 25 of the images present in this dataset. So if you run this every time, it will move and shift to the next batch and show you the images in that batch. So at a time we are just putting 25 images. So these are the from the CFAR dataset, not from the ImageNet. Okay. Oh, I didn't share the link. Okay. Just a minute. Yeah, I've shared the link of the code. Yeah. So when you are running, you would want to switch it to the GPU, like here, change runtime type to GPU, and run all of those device from these lines. So once you have shifted to GPU, this should give out CUDA. If it was not, it will return CPU instead. So here we are viewing the dataset, and so now we are defining our loss function. So here we are using the regular cross entropy loss, because this is now a classification task. So we are back to cross entropy. Same our Adam optimizer, and this is the training process. So now when this training process is happening, because we defined these layers later, and for these last few layers of our model, we had not set this requires grad parameter as false. So when the training process will happen, only the weights that are connecting these layers, they will be getting updated. The rest of them will be same, they will not change. Okay, so that is the part which is actually making sure that you are doing the fine tuning. So it's the same part as we saw. So when we want to upload our, since we have uploaded our model to GPU, we also need to upload our targets and the data. They should also be uploaded to GPU. So you can, any general quantity in your code, if you want to upload it, push it to GPU, you do it with this thing. Okay, so to device, so any variable dot to device. So any tensor can be pushed to GPU. Then we are doing the forward model. So this also, as we saw in the previous question, this model will also have that forward function, since it is implemented in Pytorch. And when you pass in data as input, it will give you out the probabilities of it belonging to each of the classes, and the targets you also have, since you are taking those from the dataset itself, and you will check the loss between those, and for printing purpose we are appending that loss. And before we update our gradients, before we update our weights, we need to set the gradients back to 0, calculate our gradients, and update our weights. So the same process that we saw in the previous code. So once we run this, this should start running. Yeah. So as you can see here, it's not actually training the entire model, else every epoch it would take a long time to run. But since it is only training for these last few layers, it's almost like you are training a simple neural network, normal neural network only, without any convolution parameters. So that will keep on happening. So now we have kept the iterations to 50, so it will take a long time to run. But yeah, so that is the general idea. So given any input model, if you want to do transfer learning, you can follow this procedure and do it. So for now, your task is actually to, instead of this model resnet, you want to do, so from the 7th cell onwards, you want to change the procedure according to the requirement, and instead of starting with resnet, you should start with VGG model. So the only thing that to get the model, actually you can set it this way. And in fact, if you, if I'm not sharing my entire screen, I think, but if you go to Google and search for torch vision models, it will list out all the models that are available. Uh, so one of them is actually VGG, and in the, in fact, all your models that you studied in the course, Google Net, and all of them are available in the Pytorch inbuilt. So okay, I made a mistake here. So it's not capital VGG, it's small VGG, and the version that we saw in the course was this VGG 16. So with this you can get that model. So instead of, so maybe, okay, this seems to be learning something, but not much. So we started with some loss of around 1.8, and it has gone down a bit, but yeah. So we didn't have to train anything almost. I mean, this is compared to the real data set, we already had the convolution part sorted. We are only training for the last bit of it. So this is still less work for us. So I will stop running this part. You can actually also check the accuracy once you have trained it for some time. Maybe I should not have stopped it, but fine. You guys can now try to implement this VGG model. So you need to be careful when you write this part. Okay. So here you are setting everything for model resnet. So just instead of that, set different things for model VGG variable, and wherever later down in the code, wherever you are seeing model resnet, just convert it to model VGG, and then you can run the data, run the training. So I will wait for some time, and then we will discuss the solution also. So yeah, we'll wait for some 15 minutes for you guys to try out, and then last 15 minutes we can then discuss the solution. Any doubts at this point?
Uh, Mr. Vinod, I don't have any doubt, but actually, no, I haven't yet got familiarized with this thing. Uh, One other instructor was using actual MATLAB. MATLAB, okay, so I'm somewhat familiar, but this also is not so much difficult, but actually I haven't concentrated. Okay, so I thought that I will see these things a little bit later. So I may not be participating now. Okay.
Yeah, no problem, no problem. I mean, you later when you want to look back, this lecture will be uploaded to YouTube and you can check it.
Okay, okay, okay. Thank you. And then I took the copies of these things also in
Yeah.
my drive.
Yeah,
Okay, so
yeah,
I think I just followed your demo,
yeah,
and when time, see, first actually I have to see this Python also. I am not at familiar, and this particular software also.
yeah,
Then I will. Okay.
yeah. No problem, no problem.
Thank you. Thank you.
Actually, in fact, my goal with doing these demos is actually basically to introduce these softwares.
Yes, 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 yes.
So
See, this is correct only. And as far as possible, I followed your step by step, the functions and then modules. Okay, I will, but I need some time for me to get familiarized.
Yeah, no problem.
So
Absolutely no problem.
even then I cannot do it. Okay.
Yeah.
Okay. Yeah. Thank you.
So we will wait for 15 minutes for if someone else wants to give it a shot, and then we will move to the solution of this. At this point, if anyone has any doubts, you can ask freely. No problem. Mm, can I get some feedback for the session? Like, how do you guys feel this code demos and some small part for you to try out this type of sessions? We have only 3 participants, I guess. Yeah, no problem. I mean, it's all just to introduce the aspect. I mean, in the course you get to learn the theory behind the stuff, and I'm just trying to introduce how you would go about when you are implementing it. I mean, as long as you are following the explanations, you can play around with the code later also. And because in practice, ultimately, it will boil down to actually running train, like writing your own codes and running these models. So I felt like introducing it will be a good idea. So so in that case, I think then should I directly jump to the solution? Okay. So yeah, my screen is visible. So as we did here, we have now set a new variable for the VGG model, and with this we are taking the pre-trained VGG model on the ImageNet dataset, and we are setting it here to model VGG. Okay, maybe because of a RAM issue. along with Google Meet. Just give me a minute. The RAM seems okay. Okay. You can still try running this. Oh, I have to restart the console. Ah, okay. I will just run through the entire code again. Mm, yeah. So with this we got the VGG model, okay, and we want to see what is in the model, what are the layers in it. So we can print this VGG, and you will see that uh, the last almost the entire model is full of convolution layers, but at the end of it you have this classifier and average pool layer. So these are the two layers we would want to switch and put our layers there, okay. The rest of the network we want to keep same. So I'll just copy this part of the code, and instead of ResNet we will have model VGG, and we are going to set, with this we are fixing the weights of the model. The average pool layer we can fix to identity, but this is to be done for model VGG. So I'm changing that, since there was no fully connected layer here, so you can actually remove this part, or maybe we can just replace this with classifier and remove this. Okay, so what I just did was I reinitialize this average pool layer to be an identity, because I don't want anything to happen over there. I replace this classifier layer with the same thing that I basically put for our ResNet, and yeah, that's it. Oh, I'm still printing the, so instead of that I should put VGG here. Yeah, so this is our new updated VGG. As you can see here, the average pool and classifier layer, they have been changed. They are what we set here, the same thing that we set for the ResNet. And then we are just loading our data set. We can plot it if you want. And yeah, this loop will stay the same, but instead of ResNet we would want the model to be model VGG, right? And here also, okay. And once we have switched it to that, we can run this thing. So now it is trying to train the VGG model instead of the ResNet. It will still look the same, but maybe we should have reduced the number of epochs. I will just change this to maybe 10. So that it will just run faster and we can see the results quickly. So while this is going on, maybe I will discuss what we are doing in this part. So we are basically checking the predictions of each of our for so from this train data set we are just picking some of the examples and we are checking the prediction of the model for those, and so the class will be determined by which of them is the maximum probability, and that's how we are getting our predictions. And if the prediction and the real label are same, then it's a correct classification, so we are adding that up, and we are going to divide it by the total number of samples and we'll get the accuracy of the model. That is the idea. So it's almost 4, so 5 epochs have completed. We'll wait for a little bit more. At this point, whatever you have learned from the course, with that I think there are many fun tasks that you can try and explore. So have you guys heard of style transfer? Okay, so these in different apps like social media apps, you will see that there are some filters, right? So in if you take a photo and you apply that filter, it will put something more which is not already present in that your photo, but it will add something or maybe change the way the photo looks. So there are some filters which will make show you how you would look as a animated character. So that is actually called style transfer. So this, you can actually from whatever you have learned so far in the course, you can kind of try and implement that also and train your own model for that. So you can refer something called this neural style transfer, and then you will find some YouTube videos about that. That will this and the codes that we are seeing here, with that you can implement style transfer also. So far the course has actually moved on quite a lot, and you can do many fun things with the content that you have learned. So our 10 epochs have finished, and we are at the loss has reduced to 1.01. It started with 1.15. Okay. So we didn't have much training to do is the point. So even with such a little training, you will see that the accuracy will be decent. I didn't train the I didn't train the resonate model. I trained the VGG model. Yeah. So we'll check the accuracy of the VGG. It will be somewhere close to 60. Yeah. So with this little training amount of training, also we are getting a 65% accuracy on our training. If you want more, you can run it for more number of iterations, and that should do. And you can in fact even do some more modifications by changing this later part. That's the idea. Okay, so that concludes the second demo also. Uh, yeah, that's it. So if you guys have any things that you would like to see in the next week, maybe you can let me know. I'll try to see if that I can prepare something for that material. Have you guys had a chance to look at the week 8 content? Okay, no problem. Maybe I will. So week 8 is mostly on these these sequence-based models. So RNNs, LSTMs, so all of that stuff. So with that you can actually uh, some codes that we can actually work with would be something like audio data sets. So we can actually classify different types of music genres, something like that. So if you guys want, I can try to prepare a demo for that. Okay. So yeah, that's it. I mean, if you have any doubts, we can cover those, or yeah, the session is we can conclude today's session. No doubts. Okay. Yeah, sure. Yeah, sure. Ocean, if you do you have any doubt? If not, then okay, we can conclude the session. I'll stop the meeting.